Yes, so hello everyone, big welcome to the Manju's Electro Hive channel. Here we talk about tech, electronics, and tech advancements here in Uganda. So I'm Joseph Oklang, I'm a biomedical engineering student, and I'm going to be taking you guys through all you need to know about resistors today. So here we shall be talking about what a resistor is, how they are used, how they operate, the different types of resistors that are there, how you would read the different color codes, the value of a resistor from its color codes, and from the high power resistors, um, how you can easily determine which resistor you want to use for a particular application, and different kinds of variable resistors, and which uh, type of resistor you'd also actually choose for particular application. So without further ado, we can now get started. So what is a resistor? So in the layman's language, a resistor is basically a device that you'd want to use in order to limit the amount of current that you want to be flowing in the circuit, and probably get a voltage drop, maybe which you need to power on a certain device. So here in the definition they're saying resistors are electrical devices that act to reduce current flow and at the same time act to lower voltage levels within circuits. That is true. So the relationship between the current and voltage levels in a resistor are given by the Ohm's law equation, which is V equals to IR, which you're seeing here. So there are very many applications of resistors. The simplest application that I can give you is practically when you're dealing with when you have your battery. You have your battery here, you have an LED. Let's say you connected an LED here. Then you'd want to put a resistor in order to limit the amount of current that is going to be flowing through this LED, because if you just connected the LED direct to the voltage, you can easily blow it. You can easily blow this light emitting diode. So the best thing to do is connect a resistor to limit the amount of current that is going to be flowing through it. But here you can see that there are very many applications of resistors, like operating to set operating current and signal levels, provide voltage reduction, precise gain values in precision circuits, act as shunts in ammeters and voltmeters, and very many others, provide feedback networks for amplifiers. So you find that there are very many there are different types of resistors. There are fixed resistors and there are variable resistors, but then there are also these special types of resistors like the photoresistors and the thermoresistors. So we shall talk about all of these types of resistors. So here you can see these are the common types of resistors you'll see. We shall look at them. Then you have potentiometers and trimmers. We shall as well look at this as well. Then these are the thermoresistor and these are photoresistor. So we're going to look at all these types of resistors as well. So how does a resistor work? So basically you have electrons flowing in your circuit, and they have and these electrons are flowing in your circuit, they have a lot of energy, not so. So here you see that the job of a resistor is to absorb some of this energy and send it elsewhere. So you find that as these electrons are flowing through the circuit, when you connect a resistance, basically what is going to happen is when you connect a resistor to your circuit, these electrons as they're flowing through the resistor end up colliding with some of the atoms, because you find that for these different types of resistors, they have different materials they're made of. So basically, if you have one that is made out of carbon atoms and all that, so these electrons will be colliding with the carbon atoms, and hence during this collision they lose some of their energy to the carbon atoms, and through this as well, this energy can be, remember, as this during as the atomic vibrations are happening. I don't know what's wrong with my voice today, but as these atomic vibrations are happening, these vibrations can be transmitted to the air molecules that are outside. So this energy is lost outside as well. You can say that maybe through radiations and all that. So basically, so as these electrons are flowing through a resistor, they keep colliding with other atoms that are the resistor is made out of, and of course, as these things keep vibrating, they keep passing on the energy to the surrounding air molecules that are around. So in that way, the resistor absorbs the energy of the electrons, making them weak, and so you find that fewer electrons will be able to flow through that resistor and all that. So that is what is basically happening here in this diagram that you can see here. So this is just showing you that there are some resistors that are made up of carbon composite, like a carbon composition resistor, metal film resistors. This, you're going to see all this. So the basic resistor operation. So here you can see a resistor being used as what? A current limiter. So what does that mean? That is what I just explained to you guys about using an LED. So you can have a resistor load, which can either be an LED, a bulb, or anything that you've connected to your circuit. So you just plug in a resistor in order to limit the amount of current that is flowing through that circuit. So looking at this diagram here, so as we increase the amount of what? Resistance. Remember this resistance, current against resistance. So as we increase our resistance, you see that the current is decreasing gradually. Are you seeing? As you increase the resistance, the current is decreasing. So that is how a resistor helps to limit the amount of current that is flowing through. Okay, you can just see it from the equation, which is V equals to IR, and to derive this thing, then you just make either subject to be V over R, not so. But for this case, we have the resistance R and the R of the load, which could be a LED or something. So that's how this equation comes about. So here, as a voltage divider, so there is a formula for voltage division also, which is this voltage division. But then when you always see a resistor with an R on top, just know that that's a variable resistor, which for now we can call a potentiometer. And so when you look at this circuit here, we have a V out, not so. So we see that as we increase our resistance, our variable resistance R2, we see that our voltage increases, not so. So as we increase R2, the potential, the voltage here increases, since V out from our formula is the same as R2 divided by, for voltage division we just say the resistor, we are determining its voltage R2 divided by R1, the sum of the total equivalent resistance, times the supply voltage, which is V in. So that's how we get the V out. So you find that as you're increasing the resistance, our voltage increases. Voltage is the pushing power of the electrons. So as you keep increasing what is limiting the electrons from going, you find that you'll need more force in order to push those electrons. That's why our voltage is increasing here. So when you look at this, for this case we have R1 here. So you find that if we're finding the V out, for this case you find that as you increase R2, our V out is decreasing. This is supposed to be actually R1. It's supposed to be R1 because R1 is our variable resistance. So as you're increasing R1, our V out is decreasing. So there will be more, as you're increasing this resistance, there will be more voltage needed to, remember the voltage drop across here plus the voltage drop here should be able to give you this. So now if you keep increasing this resistance, more voltage will be needed to push the electrons through this resistor, and so the voltage here will decrease. More energy will be sent here in order to overcome this higher resistance. So I hope you guys have got that. So as a current divider as well, you find that as you increase this resistance R1, as you remember, current flows through an area of least resistance. That is like to say, if we have a circuit, we have a resistor here, then we have a short circuit here. So you find that when the current I in comes in from here, most of it goes through this side, because here there is a lower resistance. Probably theoretically you can assume it's 0, but of course in real life we know that there's always going to be a resistance. Even in the short circuit, in the wire itself, there's going to be a resistance, but theoretically you can assume the resistance here is 0, and so the current will choose to take the path of least resistance. So if we increase this resistance, most of the current will choose to pass through here. That is how it is. So, and this is what this graph is trying to explain. So as you increase your resistance R1 here, as you increase R1, our I2 is going to be increasing. That is why you have this I2 increasing. Then your I1 will be decreasing. Most of the current will want to pass through this side instead of passing here. Who would want to go through where there is a lot of resistance? So that is how smart current is. So there are different types of resistors, of fixed resistors. For this case, we're going to look at variable resistors as well. So you have the most common two types, which are carbon field resistors and carbon composition resistors. The most common type I've actually seen is this a four band cord resistor, which is commonly, this is the type that I always see. So these are the different power ratings and resistance that in most cases they lie around. So for these two, you can see that. So then there's a metal oxide film, then there's also a precision metal film. These are rare ones I've not yet seen. Then there are these types of resistors as well, high power wire wound resistors, which are majorly used in high power applications. Then you have these special type resistors. You have photoresistors and thermistors. Photoresistors and thermistors. So you find that a photoresistor is light sensitive. So as you increase the light level, the resistance decreases. And of course, what happens when the resistance decreases? So when when you increase your light level, the resistance decreases, and of course more current can easily flow. So you can use this application in order to maybe power up something. Maybe you can put in a BJT close to it, and whatever happens, that can be used to control another circuit. So this resistor is actually very important. So you have a temperature sensitive resistor, which is a thermistor. So as you increase the temperature, the resistance decreases. That is how a thermistor behaves. So how do you take readings of or how do you understanding resistor labels? How are you going to take the readings of this? So resistors use either series of painted bands, that is called color coding, or written labels, as you can see here. For this high power wire wound resistors, you find that they already have their labels. But in most cases, the carbon composition and this metal oxide carbon film resistors are small, in that they can't really write the particular resistor value of that resistor, so they just use color codes. So as I told you guys, the most common type I found is a 4-band resistor, where in most cases, that's what we have done in our practicals at SEDAT and as well during intern. So here, the first color code will be your first digit, the second color code will be your second digit, the third one will be a multiplier, then the other one will be the tolerance. So that is what happens when you find your 5 color coded resistor. Don't get scared, just go on Google and check how they have aligned out this. So you see that this is the first digit, second digit, multiplier, tolerance, and reliability. But then for this, you see that the first digit second digit, third digit, multiplier, tolerance. So depending on the type of resistor you have, there's a different way in which you're going to obtain its value of resistance. But for the 4-band color-coded resistor, that is going to be very easy. So there is a simple way of memorizing this table, so which is that black boys rape our young girls, but violet, remember violet is almost the same as purple in color, but violet goes willingly. Then these are the last two, which is the tolerance. So let me give you guys an example. During in turn, we had a resistor. Just pardon me a bit for my drawings. So you had a resistor. Here was an orange. Even this was orange. I think I should just better use. Sorry for that drawing. I'm just trying to. So let me just get an orange. So here you had orange. Here you had orange. Then we had a black. Had a black here and a gold. For the gold, I'm just going to use yellow. So you had a gold there. So how do you read the color code of this resistor? So here you have orange, first, second digit. So orange, where is orange? Orange is here on 3. So 3. Then the next one is as well as 3. Then this one here is a black, which is the third one is a multiplier, remember? So you're going to multiply this times 1. So after multiplying it by 1, the last one was gold, not so? So you're going to come to gold. So it's going to be you're going to come to gold. Gold is going to be tolerance. The last one is tolerance, not so? So gold is going to be a plus or minus 5%. So we have a 33 ohm resistor plus or minus 5%. So you're going to, it may either be maybe 34, maybe a 32. So whichever value, 5% of this, then you add it here or you subtract it from here, will be the value of your resistor. It will range within that. So what here now we're going to talk about the power ratings for the resistor. So it's important to note that you can have two resistors of the same values and yet they have different power ratings. So what is the importance of the power rating? So you find that when you have a resistor of a higher power rating, it's capable of dissipating the heat generated by the current more effectively as compared to if it had a lower power rating. So you find that if you replaced your resistor which had a higher power rating with one that had a lower power rating, what would occur is called a meltdown. So you find that your resistor will just burn up because it's not able to dissipate the heat as well as the previous resistor that had a higher power rating. So for this case, how can we possibly calculate the power rating of a resistor before we actually use it in a particular circuit? So here we have an example. So we have, as you can see in this diagram, we have a current of 0.01 and then a resistor over 3300 ohm. That's how they read dollars, 3300 ohm. So from this equation, which is P equals to I squared R, which is called the power law, using the power law, so you find that the value you get is 0.33 when you insert this current value, which is 0.01 squared times the 3300 ohm, you get 0.33 watts. So when you're using when you get 0.33 watts, so that's the power rating of the resistor that you want to use in your particular circuit. So what you find out is, if you have a power rating of 0.33 watts, so you want a resistor, so you want a resistor which can handle this or more, else it will what? It will have a meltdown. So notably, if you're dealing with AC currents and voltages, you'd want to use the RMS values of current and voltage. So you can use these different equations in order to obtain the power rating of your resistor. So now let's talk about, we're done talking about fixed resistors. Let's talk about the variable types of resistors. So you have here a potentiometer. There are potentiometers, rheostats, and trimmers. So potentiometers like this, potentiometers are majorly found in what? I don't know if you guys have opened up a radio, its knob. You find this kind of device in the knob. So the plastic knob is just connected in front here, but this is basically the whatever device that is inside there. So you find that a rheostat is basically the same as a potentiometer, but they have a small difference in that rheostats are used specifically for high power AC electricity. That is where rheostats are applied, and potentiometers typically are used with low level DC electricity. So both potentiometers and rheostats are designed for frequent adjustment. But then trimmers, on the other end, are miniature potentiometers, and they are found on what? Circuit boards. In most cases, you can be able to solder them onto your circuit boards, and in most cases your circuit board is enclosed, so they are not really meant to be adjusted frequently, but they are used for fine-tuning circuits, and they are usually hidden with a circuit board enclosure. So that is basically what trimmers are. They're just miniature potentiometers, and they are found in the printed circuit board, which is of course always, in most cases, enclosed in a device. So when you have a toy car, okay, maybe not necessarily a toy car, whatever device, maybe your headsets, and if there's a variable resistor there, it's probably enclosed because you don't need to adjust it frequently, unlike a potentiometer or a rheostat. Potentiometer, which you find in your radio knob, which you always have to adjust. So that's the basic difference between a potentiometer, rheostat, and a trimmer. So when there's something to note here as well, we're almost done. When purchasing a variable resistor, you should make sure that you understand the distinction between a linear tapped and non-linear tapped variable resistors. So the meaning of a tapper is basically describes how resistance changes with the way you're adjusting your knob. So if you're adjusting it very fast, how basically is your resistance changing with how you're tuning your knob, your radio knob or something. So there's what you call linear tapped, then there's non-linear tapping. So for linear tapping, as you keep adjusting your knob, the resistance also increases linearly. But for a non-linear tapper, as you keep adjusting your knob, first it starts slightly slower, but then at some point it begins increasing rapidly. So that is how. So then why would we choose a non-linear tapper over a linear tapper? So this basically comes in form of the human physiology. So it turns out human physiology has a weird way of perceiving changes in signal intensity, in that if such as sound and light intensity. So if you find that if you doubled the amount of light, or if you double the intensity of light, or the loudness of sound, you'd probably assume that we perceive it the same way, in that if you double the light intensity, we would perceive it in that the brightness of whatever, maybe your torch or headlamp, is recognized as doubled by your brain. but that is not necessarily what happens. So basically what we do is we use non-linear circuit. We use non-linear tappers, in that perceived loudness or brightness is proportional to log 10. So in case you're building an amplifier for a set of speakers or building a home light dimming circuit, it would be wise to use a variable resistor with a non-linear tapper. So yeah, that is basically it. So you need this when you're adjusting the brightness of whichever device you're using. Our eyes don't perceive a double in brightness as necessarily a double in brightness. So you may put a double, then this side it should be like a triple. That is how we perceive we perceive a triple as a double in the intensity of light. I hope you guys have understood that. So that is why we basically try to use a non-linear tapper variable resistors. So basically that is all we had to learn about today in terms of resistors. So thank you very much guys for following through. Yes, so I hope to meet you guys in the next video. Thank you. If you like the video, please give a thumbs up, and hope to see you guys in the next video. Thank you very much. Have a nice and blessed day. Be up.